Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In today's video, I want to talk about Jordan canonical forms and invariant theory. So what I would like to do is to revisit this theory of Jordan canonical forms as a way to illustrate some of the rather interesting and subtle phenomena that can take place in invariant theory. And in so doing, we'll also get a better appreciation of why Jordan canonical forms are rather subtle, and in fact the subtleties in the two are reflected in each other. Okay, so let's look at our main example. Okay, so when you do Jordan canonical forms, you usually work over some algebraically closed field, which I'll denote by K. Okay, so we have the set of n by n matrices. You look at square matrices over this field K. I'll denote that set by m. So as space, it's just the same as n squared dimensional affine space. And of course, on this set here of n by n matrices, we can conjugate by invertible n by n matrices. So the set of invertible n by n matrices, GLNK, that's G, that acts by conjugation on M. Okay, so we are in the situation of a group acting on a affine variety here. Okay, so what you're interested with Jordan canonical forms are of course similarity classes. And by definition, we've set this up so that these are precisely the G orbits of this action G on M. Okay, so what's the point of Jordan canonical forms? Okay, so what's the aim of that? Okay, so basically the idea is as follows. You start with a matrix, okay, and then you look at its similarity class. So really it's the similarity class that's important. So you pick some alpha inside this M mod G. Remember, this is the set of G orbits, this is quotient space, okay? You pick one similarity class, and then what you want to do is in that similarity class, you want to find a good representative. So you pick some actual matrix A, so that's inside M, and that's going to be representative. So if you look at the G orbit, the similarity class of that A, it is the original alpha you came up with. Now, of course, this A is not unique when you do the Jordan canonical forms, right? You have direct sum of Jordan blocks and you can permute them around, but it's a very small set compared to the whole orbit here. Okay, so to prepare ourselves for thinking of this in this invariant theory and the geometric perspective, I'd like to recast this aim, okay? So basically the thing that you want to do here essentially is have a function which maps this alpha inside M mod G to this A inside M. So what you want, so to speak, is a section, or perhaps more generally a multi-section. So that's a map sigma from M mod G to M, and it's a section of the quotient map pi from M to M mod G. Okay, so let's just pass this properly. Okay, so remember, you've also always got a quotient map when you're in the situation of a group action. Okay, so any, in this case, matrix inside here, you can send it to the corresponding G orbit, which is the similarity class containing that matrix. Okay, and we want a section of that. So what's section mean? So it's a map like this, okay, so it's a map like this alpha to this A, and to be a section means that you want the composite, this sigma from M mod G to M, composed with this M to M mod G, so it's a map from M mod G back to itself to be the identity. And this here just represents this equation here, okay, so to see that, okay, you start with this alpha inside here, you map it to the A, and of course, G dot A is the map from that's given by pi, and you want this G dot A to equal alpha. So that's the original one. So it's the identity on alpha is this, well, alpha maps to A, and then you send it to this pi of that A, which is G dot A. Okay, so if you do the sigma first, and then the pi, you get the identity. Okay, so if we want to be able to come up with something like this, of course, we need to understand this quotient space really, really well. Okay, so that's one of the things that you need to do. Okay, so we'll have a look at that. Now, of course, as I said to you, this A is not unique, and usually there are several values, so maybe it's better to speak about a multi-section. So instead of being a properly defined function, so each input here gives you one output, maybe you should have a small number of outputs here instead. Okay, but that's roughly what's going on, and that gives you a motivation for the importance of this M mod G. Okay, so let's look at the geometrics perspective and see how we handle this M mod G from the point of view of algebraic geometry. Okay, so let's look more at the general setup. So we have G is some reductive group, okay? So it's like a finite group in the characteristic 0 case, or something like this, GLN K. And we let it act on some affine variety V. Okay, so here, this is just n squared dimensional affine space, so that's a variety V. And remember, the way we try to approach this quotient is dually using the coordinate ring. So this V has a coordinate ring, K of V, that's some algebra over K, that's finitely generated. And since we're looking at the dual of taking the quotient is to look at the invariant ring. So we can certainly G, since it acts on V, also acts on this coordinate ring. You can look at this invariant ring, and then you can use that to define this coordinate ring here, okay? And the reductivity allows you to conclude that this is a finitely generated algebra, so this corresponds to some variety here. Okay, so let's look at this setup. And so remember how this gives you something like a quotient morphism. Okay, so firstly pi, there's a map pi from V to V double mod G. Okay, so I don't use the usual single line here because at the moment we don't know it's the quotient space, okay, in the sense that the points correspond to G orbits, okay, and we'll show in a moment how that's actually not the case. Okay, so we have V maps to V double stroke G. Okay, so where's that come from? Well, to get a map like this, we just need a map on the coordinate rings in the other direction. Well, the coordinate ring of this is this invariant ring, and that's a subring of K of V. So it's a subring of that subalgebra, so we get a map this way. Of course, since it's the G invariant, this is actually G equivariant, if G acts on this the usual way and trivial on here. But most importantly, this is continuous. Okay, so what does continuity of this map mean? Okay, well, it means that the inverse images of closed sets is closed. So in particular, the inverse image of a single point is going to be closed. Okay, easy enough. And what you would like, if this is to be the quotient space, is that the points of this should correspond to G orbits. Okay, so how should they correspond to G orbits? It should be that the inverse of any point inside this V double mod G is actually a G orbit. Okay, and what I want to show you is that that's unfortunately not the case. So this is one of the subtleties of invariant theory that occurs because this group here is infinite. Okay, so let's look back at our main example. So rather than for general V, we go back to our M, which is n by n matrices, and G is GLN. So, and we'll pick n equal to 2. So we look at 2 by 2 matrices. So here's a 2 by 2 matrix. Okay, zeta here will be just some fixed scalar. And this epsilon will be a non-zero scalar which we allow to vary. Okay, so here we have 2 by 2 matrix. And of course, what's its Jordan canonical form? It's this one here. It has zetas on the diagonal, and it's got a 1 in the upper right-hand corner. Okay, so that's easy to see that, of course, the two eigenvalues are zeta here. Okay, but this is not diagonalizable. Okay, so of course it has to have this Jordan canonical form. And since it has this Jordan canonical form, it means that all these matrices for every non-zero epsilon is actually in this G orbit. Okay, they're all similar to each other and similar to this one. And what we're going to do now is we're going to look and see what happens as you let this epsilon go towards 0. Okay, that's easy enough. So we just replace the epsilon with 0, and what do we get? You get this scalar matrix. Okay, this is a scalar matrix. Okay, and of course, being diagonalizable means that it's not similar to this Jordan form here. Okay, so that means that it's not in this G orbit. Okay, so here we have some matrices, and they sit inside this G orbit. Okay, and we move in this G orbit, and as we go towards epsilon equals 0, we get outside this G orbit. We get into a different G orbit. Okay, so what's that mean? That means that in particular this G orbit here is not closed. Okay, if it were closed, then as you take the limit, it should stay inside there. But that's not the case. Okay, it goes to some other G orbit. Okay, it's the G orbit containing this, which is just this itself, and so it's not closed. Okay, so let's try to understand this. Okay, this is a very, very important, interesting phenomenon. Okay, so if you look and see what happens with pi in this case, okay, so it maps matrices to their similarity classes, what's going on here? Okay, so here you have some orbit, right? And of course, since this is G-equivariant, this orbit will map to a single point. Okay, so this maps to a single point. And since it's continuous as well, it means that anything on the boundary of this orbit, okay, anything in its closure is also mapped to that same point. Okay, in particular, this one here. Okay, so if this one here is mapped to the same point, then in fact that entire G orbit is mapped to the same point as well. Okay, so that means we have two G orbits, the one containing the similarity class containing this Jordan form, this 2x2 Jordan block, and this similarity class consisting of this scalar matrix here. Both these two G orbits get mapped to the same point inside this M double mod G. Okay, so if you take the scheme quotient defined in this way, then unfortunately one of the points corresponds to not just one orbit, but it has at least two orbits, and in fact these are the two orbits. So in particular, one way to state what's going on here is that pi doesn't separate all the orbits, okay? So we'd like the points here to correspond to the different orbits, but unfortunately that's not quite the case. One of the points corresponds to actually two orbits, and pi, this map here, doesn't distinguish these two orbits. So that's just one of the features and the interesting phenomena that occurs when you define the scheme quotient in this way. And we'll see in a moment how that reflects the subtleties in Jordan canonical forms. What's going on here, which makes the theory of Jordan canonical forms rather subtle, is the fact that there is actually no natural scheme or variety M mod G whose points naturally parameterize the similarity classes. Okay, so the best you can do is this M double mod G, and when you have this M double mod G, some of the orbits get identified together. Okay, and this occurs because some of the orbits aren't closed. Okay, so we don't have a scheme M mod G, but we do have this M double mod G, and it's good to know what is that. Okay, and this will tell us a lot about the theory of Jordan canonical forms. So let's start by setting up the notation so that I can describe what this set is. We'll start with the set P, which consists of monic degree n polynomials. So here you have a monic degree n polynomial, and these are in bijection with what? With the points in affine n space. Okay, so let C be the bijection from AN to P, which sends this vector zeta 0 up to zeta n minus 1 to the corresponding monic polynomial with these as coefficients. Okay. Now we want a G equivariant map from M to M double mod G, so I'm going to give you something which plays the role of this M double mod G, a G equivariant map, which is the one here. Okay, and it also mimics what you do when you do Jordan canonical forms. Okay, so the first thing you do is you look at the characteristic polynomial. Okay, so now we can interpret this as a map from M to this set P of monic polynomials. Okay, of course, depending on how you define the characteristic polynomial, you may need to multiply by a sign to make it monic. So you can take the input a n by n matrix, you spit out its characteristic polynomial, change so that it's monic, and then you can apply the C inverse to map to AN. Okay, so here you have a map from M to AN, which just pulls out the coefficients of this characteristic polynomial, and this is G equivariant. Okay, so just like the map from M to M double mod G is G equivariant, this one is too. Okay, so what does that mean? Remember, G acts on M by conjugation, and it acts trivially here. And to say it's G equivariant, well, let's just check. If you input some matrix, it doesn't matter whether you conjugate it by something, and then you apply this, okay, characteristic polynomial, map it to here. Or if you just take the characteristic polynomial, which is the same, because this is a similarity invariant, and map it to here, and then you act, which is a trivial action, which doesn't do anything. Okay, so those two composites are the same, so this is G equivariant. Okay, so what's the theorem? The theorem says firstly that this M double mod G is actually isomorphic to affine n space. So here you have affine n squared dimensional space, and this M double mod G turns out to be affine n dimensional space. So it's isomorphic to this, but what's more, you can actually really lock down what is this morphism as well. Okay, so when you lock down this morphism, you can also say what the fibers will be. okay? And so the point is that not only do you have this isomorphism capital phi here, but this diagram here commutes. This map from M to AN is this phi, and this is the quotient map. Then the isomorphism between these two makes this diagram commutative, okay? So of course, this is a diagram here. If you want to understand it in the dual picture on the coordinate rings, you can do that too. And that's often an interesting thing to do. So let's just have a look at that. Okay, so this is n squared dimensional space. Its coordinate k of m is given by n squared variables. And the variables just basically pick out the entries in your matrix. So you can make the variables a11, a12, all the way down to ann. Okay, they're just the coordinate functions on each of the entries. Okay, so the n squared of them. And then you can look at kmg. Okay, so you can let the group act by conjugation on here, and hence conjugation on all these variables. And you can say, what are the invariant polynomials here? Okay. Well, basically, because of this commutative diagram, it essentially comes from here, which is the characteristic polynomial. And you want to look at all the coefficients of the characteristic polynomial. And what are they? They're basically things like the trace of the polynomial. So that corresponds to the polynomial a11 plus a22 plus all the way down to ann. All the way down to, well, the last one is essentially up to scalar, the determinant. So you can look at this polynomial in these n squared variables, the determinant of a11 down to ann. So that's a degree n polynomial in these entries, okay? And then of course you have all the ones in between, which correspond to the elementary symmetric functions of the eigenvalues, okay? So what this theorem is saying is basically, well, it's quite easy to check that these are invariant polynomials, and in fact these n polynomials generate this subring, this invariant ring, and in fact they're algebraically independent. So this being the coordinate ring, when you work out what is the corresponding algebraic variety, since it's a polynomial ring in n variables, that is an, and that's how you get the isomorphism, and that's the interpretation on the dual side, okay? So once we have this theorem, we can see very clearly what's going on in this picture, okay? So firstly, this map pi, remember, it doesn't separate orbits. Some orbits get smashed together, okay? And which ones are those? They're precisely the ones with the same eigenvalues, so the ones with the same characteristic polynomial, and hence the ones with the same eigenvalues. Okay, so if we fix a set of eigenvalues or a characteristic polynomial, of course, you could get different g-orbits representing that. Okay, so fixing the element inside here, which is a characteristic polynomial, okay, and then you want to look at the inverse image inside here, pi inverse of a point. Okay, so that's the same as phi inverse of the corresponding point inside here. Okay, so basically all the matrices with that given fixed characteristic polynomial. Okay, so of course, if you look at all those matrices, that's a union of similarity classes, and they're all the Jordan forms. Okay, the similarity classes of the Jordan forms, which have those eigenvalues, okay, those given eigenvalues. And there's only a finite number of possibilities for what those Jordan forms are, up to permuting those Jordan blocks. So this inverse of a point, okay, so even though it doesn't separate orbits, okay, so the fibers aren't just single orbits, the number of orbits is finite, okay, so the amount of gluing of these orbits is not so great, okay? It's only at most a finite number of orbits are in each fiber. Okay, so this mimics exactly what you would do when you do Jordan canonical forms, okay? So when you try to work out a Jordan canonical form from a matrix, what do? You look at the similarity class, so you look at this, and you work out what it is in here, which basically means work out its characteristic polynomial. And the subtlety of Jordan canonical forms is the fact that, well, once you work that out, that corresponds to a finite number of g-orbits. So then you have to find out which g-orbit it lies in, and that's a separate sort of a question. Okay, so of course, when you study this linear algebra, usually the first thing you look at are the diagonalizable matrices. And just the fact that they're interesting from that linear algebraic point of view also get reflected in the geometry? And the answer, interestingly, is yes. Okay, so I want to give you the geometric view of these diagonalizable matrices. Okay, So to understand that, we have to look at the following little fact. Okay, so suppose we have some G orbit of some matrix, some similarity class. Just imagine it like this. So this sits inside our M, our n squared dimensional affine space of n by n matrices. So you can look at the closure inside there. Okay, you look at the closure inside there. So of course G permutes the elements inside this orbit, and since the action of G is continuous, it will send the closure back to itself as well. So that means that G has to act on the closure. So this closure is actually a G stable subset of M. Okay, so you have a G stable subset of M. That's the closure. So you can look at the boundary. Okay, so that means that you look at the closure minus this G orbit here. That's the boundary. And so that's basically, so this is G stable, so it's a union of orbits, and you've plucked out this orbit here, and then you've got a finite union of orbits. And pictorially you can see, and it is actually true, that these orbits are smaller dimensional. Okay, so that's what's going on. That's a union of smaller dimensional orbits. Okay, so that's the fact that we have here. Okay, so it could be that these two are equal. The closure, this is already closed, in which case these two are equal. Okay, in this case, looking at this doesn't give you any new G orbits. Okay, so let's revisit the computation that we did before. Okay, so it's quite, we've got a good understanding of what this M double mod G is now. Okay, now let's look at the points of this. So each point, if you look at its inverse image, that corresponds to a finite number of G orbits. Okay, so a point in here corresponds to just basically a set of eigenvalues, including multiplicity, lambda 1 up to lambda n. Okay, so let's fix that, and then we get some fiber corresponding to that. So they're all the matrices which have these as their eigenvalues. Okay, those orbits. Okay, so you pick such an A, which is like that, and basically we're going to look at the G orbit of that. So that's similarity class. Okay, and essentially inside this G orbit you'll find some Jordan canonical form, and using the computation that we did before, we can show that the closure contains the diagonal matrix with these eigenvalues. Okay, so that's very easy to see if you understood that example well, and that's what you find here. So it turns out that if you have something which is not diagonalizable, okay, you can do this, and you'll find on the boundary is the orbit containing the corresponding diagonalizable matrix. Okay, so in some ways it's the smallest G orbit inside this fiber. So this fiber is a union, finite union of G orbits, and the smallest one corresponds to the diagonal matrices. Or more precisely, if you frame it in this using this fact, and that's the usual way that's done, it corresponds to the closed orbit inside this set here. Inside this finite union of G orbits, there's one closed orbit, and that closed orbit is precisely the one corresponding to the diagonal matrix with those eigenvalues. So one thing that we do see is that though this pi, it doesn't separate all the orbits. Okay, but what it does do, of course, as you should know, is it can distinguish all the diagonalizable matrices, the similarity classes of those. So what pi does do is that even though it doesn't separate all orbits, it doesn't distinguish them, it does actually separate the closed orbits, the one corresponding to diagonal matrices. Okay, so in this way we can see how, well, firstly, in this video we saw that this M double mod G, if you use schemes, okay, you can't always get a scheme which naturally parameterizes G orbits. So this is just one of the things about algebraic geometry that occurs, and this reflects the subtlety in looking at Jordan canonical forms. The fact that once you've taken this characteristic polynomial, you actually have to do quite a bit more, and it's a little bit subtle what happens. I hope you enjoyed this adventure in pure mathematics.